The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week we explore how science and technology can help us walk when we've lost our legs, see when we've gone blind, explore unfriendly environments, and maybe even make our bodies better, stronger, and faster than ever before. Later on, I'll speak with Ken Thomas about some of the lesser-known scientists who helped create the spacesuit that went to the moon. But first, let's look at how modern science and technology is helping people walk, run, climb, and see again. Welcome to Science for the People. I'm Rochelle Saunders. With me is Adam Piore. He's a contributing editor at Popular Science and Discover magazines, and the author of the new book, The Bodybuilders, Inside the Science of the Engineered Human. Adam, welcome to Science for the People.
Thanks for having me.
So what got you interested in the topics in this book to begin with?
Well, I've always been, I've written a lot about human resilience. I've covered, I went to Iraq, I lived in Cambodia, and I studied humanistic psychology in college. But I also have done some science writing, and as I started to do more science writing, those were the stories that really attracted me, were the stories of human resilience. And that's where I found great narratives. That's where I found the stakes really high. Stories that, interested me and drew me in. And some of the most exciting stories of human resilience are being unleashed by bioengineering. And I kept finding that, and I sort of just kept following this thread and found more and more stories that sort of related to the same theme, which is basically that, we're reverse engineering the human body and mind at a resolution that would have been impossible a few years ago. And that's allowing us to, understand it and hack into it and fix things and upgrade things, more than ever before, and unleash untapped human resilience. That's sort of the unifying theme.
This is an interesting thing that you talk about in the book. I mean, the book is broken into kind of three broad sections on the themes of moving, sensing, and thinking, but in those sections, it's also kind of broken up a little bit into the ideas of fixing or repairing, so giving people ability back that they might not have had or they might have lost at some point, but also the idea of extending human ability as well. And it seems like we always want to start with the fixing. We see someone who has lost a limb, we see someone who has lost their sight, someone who has degraded memory, and we want to try and fix that problem and give them those abilities back. But then I think because we're just the way we are, we always find and try and also figure out that way, can we extend the average human? Can we make general people better rather than just give someone something they've lost?
Right. I mean, to be honest, it was actually the opposite for me because, initially it was sort of the gee whiz stories were kind of like, wow, they can do that. They can make a superhero, a bionic man, or they can, allow people to see through walls. And when I had, originally pitched the book, I was kind of focused on human augmentation. But it's true, they are, part of the same, they're on the same spectrum. If you can hack the human body, you can restore function, but you can also augment it. But, you can't really separate the two. But, the stories that I found where it was having the most impact right now, are actually restoring lost function. I mean, there are some areas of augmenting, human beings, but, if you, when you're talking about bionics, you're not going to cut off an arm to have a bionic arm.
Right.
You're going to, that doesn't happen that much. The examples that I found where it was really having an impact were when people lost something and then they regained it again. So, I looked at both. It's really the same spectrum. Basically, what we're talking about is big data and to a certain extent, big data in understanding the human body and mind. We can understand how things work together. Different parts of the human leg, ligaments, tendons, muscles, and bones, and we can build a bionic limb that does the same thing. And when we understand that, we can also build a computer model. Using a computer model, we can build an exoskeleton that augments strength or speed. And then you can take it all the way down to the level of genetics and neurons, where we're talking about billions of variables, where, our computational power and our sensing power is still improving. So yeah, I mean, it started out, like I said, with, a lot of these stories were like, kind of, people were saying they were like, Facebook says they want to be able to allow people to, type using just their mind, right? So that's something I looked at, what's called synthetic telepathy, which is, can you really decode imagined speech? So, when I first wrote about that, some of the funding was coming from the military, the U.S. military, the DARPA, which is, their blue sky research program that kind of funds moonshots. And the guy the program manager who had initially funded it wanted he wanted people to develop a thought helmet that could allow soldiers to communicate telepathically. Like if they're in the caves of Tora Bora trying to find Osama bin Laden, they don't have to speak. They can call in airstrikes just by thinking. But, the applications of that, the immediate applications, I found would be for somebody with, Lou Gehrig's disease, who is locked in and can no longer communicate.
Yeah. It's interesting. There are these kind of couplings of some of this research where there's so much opportunity and funding that comes from can we augment humans' abilities for whatever purpose? In these cases, quite often the military purposes. And that's a great source of funding. And that funding can be put towards applications and research that helps areas or people that might not get funding to do the repair work, like you say. So I guess in a lot of spaces, that coupling is kind of useful for the fix things side.
Yeah. And, I mean, when I mentioned that chapter in particular, just because, I followed the whole story of how these research programs began and some of the initial papers. But then when I wanted to look at the impact it would really have, I found somebody who had Lou Gehrig's disease and who had volunteered to be a guinea pig to see if they could implant electrodes in his cortex and read his imagined speech, or at least allow him to type just by thinking when they, because when you have Lou Gehrig's disease, your muscles, you lose the ability to communicate with your muscles, but, those signals still emanate from your brain. So if you can pick up those signals, you can type. So, I wanted to, that was the story I ended up telling in the book, even though I also talked about the crazy, visionary military guy who wanted to, he saw some Clint Eastwood movie where Clint Eastwood controlled the plane just by thinking, and that was part of the example.
There is a very
sci-fi
allure to those ideas as well, and they feel a bit transgressive, but also really cool.
Yeah, actually, it's kind of interesting. A lot of people that I came across were actually inspired by sci-fi. They read about these ideas when they were kids, and they actually geared their education towards bringing them to fruition. And so a lot of the scientists I met actually, were big sci-fi fans. It's funny.
So a lot of this area, in particular bioengineering, regenerative medicine, this area is prone to a lot of hype. So how do we pick through the hype and the exaggeration and sometimes the cure-all claims to get at the real potential of the real science here?
Well, what I wanted to do, I looked at, there is a bunch of books that are total hype, and I found that many of them fell into two categories. There was one category which is very futurist, and that's kind of like Ray Kurzweil and we will do this, we will do that. This is what will happen. This is what it'll, might happen. This is what it'll be like. But, when I looked at a lot of those books, they don't really explain how we could do that. And if you don't have a scientific background, it's difficult to evaluate these claims. And then there's also ethical books, which, if we do this, these are the ethical problems. And that too, when I read those books, I had a hard time evaluating how realistic some of these things were. So one of the things I really wanted to do was actually cut through the hype. I wanted to understand how the human body and mind work. I've taken, I don't have a PhD in molecular biology, and I've taken science classes, but it's much more accessible now than it used to be because we understand how the constituent parts of the body and mind work together at a much greater resolution than we did before. And I found it really exciting to, talk to some of the scientists who are on the cutting edge of discovering how things work and sort of explain how they work and what we know and what we don't know so that people could read my book and then they could understand and better evaluate some of these claims. Like, for instance, with regenerative medicine, one of the things we found in recent years is how stem cells work. I mean, not that long ago, we didn't even know what stem cells are. And, we discovered them. They're the worker bees of the human body. They converge on a site and they can rebuild damaged tissue and replicate. And in recent years, and one of the things I talk about in my book is they've discovered that stem cells respond to different signals. You know what I mean? So they sent some, let's see, what did they do? I guess I forget the exact experiments, but they thought that if you put stem cells if you sent them out into space and didn't apply pressure on them, they would grow as tissue more, muscle tissue. But it turns out that that's not the case because you need to put force on stem cells for them to be activated and grow more muscle tissue. It responds to the forces around them. It responds to the environmental cues. It responds to, the molecules around it. And so that's kind of interesting. And there's one guy I talk about in my book, which is just a great story, a guy named Steve Badalak at the University of Pittsburgh. And he actually was just, he was trying to figure out, he wanted to use an artificial heart and use tissue around the artificial heart that the body wouldn't reject with the immune response. So he actually took a dog. You can never do this nowadays, but he took a dog named Rocky and he removed part of the small intestine and used it as sort of aortic tissue to see if the dog, if it could work, because I guess synthetic aortic tissue had, been rejected. The immune response of the body had attacked it. And strangely enough, the dog thrived and, he kept, the dog was wagging his tail the next day. And then eventually he did it with other dogs. And when he went in to look, there was no sign of the intestinal, tissue. And what he found was, it was a big mystery, but what had happened was the body started to break down the tissue. And that released signaling agents, these tiny things called cryptic peptides, which went out and they suppressed the immune response, which would have led to scarring and prevented this from happening, from rebuilding it. And then it summoned stem cells to the site and they rebuilt what had been intestine into aortic tissue. So, it's how the body works down to the molecular level sometimes, and how to manipulate those signals so that we can get it to do what we want. And so that's really what I wanted to dive into those things. And another thing is when I was looking at bionics, and this might sound a little incoherent, but there is a coherent theme throughout the book, even though it's many different topics. But when I was looking at bionics, it's very interesting how the human leg works. They didn't really realize before why when you give somebody a prosthetic peg leg, it causes back problems, and it uses much more energy for somebody to walk, and it's clearly not anything close to the real thing. Well, what they discovered is part of the reason is because the human leg is like a web of giant springs. And when we walk, every time we take a step, we actually, our tendons and muscles, they work together, they absorb energy and shift that energy through this web and then release it every time we take another step. So we're recycling, somewhere in the neighborhood of 50% of the energy from the previous step. And so if you want to build prosthetics, they've learned just in recent years that work for somebody, you need to replicate that. You need to make a leg that absorbs the energy and then can feed it back when you take another step.
I do want to talk about Hugh Hare because he was one of those chapters of your book were some of the most interesting to me. And then following that up with watching him walk in some of the videos that I've seen him in online is really, really just kind of amazing to see. So can you maybe give us the backstory of Hugh Hare?
Yeah, sure. Yeah. that was one of my favorite stories for sure. And it's the one that I began the book with, because like I said, there's sort of another spectrum. It's like when you're looking at reverse engineering the body and mind, it's easier to build a leg, because when you think about it, there's a few hundred tendons, ligaments, muscles, and bones, a few hundred constituent parts that make up the human leg. Mm-hmm. And, there's billions of neurons that you would have to measure and track and emulate. So I went sort of from simple to complex. So, if you think of the human leg as simple, it's not really that simple. We didn't have the technology to measure how all these constituent parts work together and model them with a computer before. And now we do. And that's what allowed Hugh Herr to do what he did. But let me tell you the story. Hugh Herr was basically a rock climbing prodigy from Lancaster, Pennsylvania. He was, when he was in high school, he was a C and a D student, and he lived to climb walls, to climb rock walls, and he went climbing with his brothers and friends, and he, there was some famous climb in upstate New York, I think, and it was called Super Crack. And nobody, people came from all around the world to try and climb it, and I think, one guy climbed it for the first time just a few years before Hugh Herr came along, and it took him a few days. He had to siege, whatever that means. I guess you camp on the wall. But Hugh Herr went, and he took pictures, and he built a replica of this in his parents' barn, and he practiced, and he climbed it, I think, just falling once in like half an hour or something. And this made him, famous throughout the country, and he was already in rock climbing magazines and all of that. And, anyway, so he wanted to go, ice climbing with a friend of his. They decided to go to Mount Washington in New Hampshire, and they set out, and, it was just beginning to snow when they set out, and they climbed, an ice wall. And, when they got to the top, where they needed to continue on to the peak, a storm had picked up, and there was like 50-mile-an-hour winds, and soon they couldn't see, and they were, it was totally overwhelming, and they decided to turn back. Mm-hmm. But they couldn't, the visibility was gone, and they, were trying to find their way back by the direction of the wind, and the direction of the wind had shifted, and they hiked into the wilderness, and they were lost. And they almost died. They hiked for days, and Hugh fell into a stream. He got his leg got wet, and they couldn't find their way out. And after 3 days, I think they settled beneath a rock, and they talked about how they were, they talked about whether they believed in God, and they both thought they were going to die. And just at the last moment, a woman discovered them. There was a big search party for them, and their lives were saved. But Hugh Herr, both his legs were amputated below the knee because he had frostbite. And so he woke up in a bed basically with two stumps, and for months he would just go to sleep, and he would dream that he was running through the field behind his parents' house with the wind whipping through his hair. And then he'd wake up and remember that he was never going to run or climb again. But he started to climb. He just, one day he got frustrated, he got out of bed, he climbed up the stair, the bottom of the stairs in his basement. He climbed onto the refrigerator, pulled himself up, and then he convinced his brothers to take him climbing, and it was like he still had legs when he was up there, and he started messing with his prosthetics. He started making them 10 feet long or 1 foot long with blades that he could slip in and become a better climber. He got a prostheticist to allow him to tinker in his workshop, and he felt totally free up there. And he got on 60 Minutes and stuff, and into more rock climbing magazines. He was even better than he was before because he had these custom made legs, and he was lighter. So but then he would come down, and the technology that he had when he was walking was just like a peg leg, which was worse than just as bad as it had been in the Civil War. So he went back to school, and he started taking engineering classes, and he was also working with a prostheticist to learn stuff. And suddenly he became a straight A student, and eventually he got into MIT. And then, now he has become one of the world's leading prosthetics manufacturer and one of the world's leading prosteticists, and what he did is basically, I'm skipping a lot of the story here, but partially he was also looking to use what he was learning about how the human body worked to build exoskeletons that could allow him to climb better. And he made a little running shoe that he couldn't use himself that recycled energy. But he learned everything that was known about the human leg, and some of the stuff I was saying before, that the leg is a bunch of springs, and so in my book I go into some of the discoveries that have been made over the last 100 years about how the human leg works. And but Hugh had the fortune to come along at a time that we're in now, when we have this unprecedented computing power and sensing abilities. And so, I don't know if you've ever seen a commercial for like EA Sports, where they have like LeBron James or somebody, and he's got these reflective silver balls all over his arms and legs. Well, yeah, that's a motion capture technology. It's also used in some movies like Avatar. And so you can put these little tiny balls on and surround yourself by cameras, and it can measure how different parts of the leg or arm or whatever move through space in relation to one another as you're ambulating, right? So in his lab, Hugh Herr had a treadmill, and first he took all the scientific papers that had been created about how the constituent parts of the human leg work together, and he built a mathematical model spelling out, if your foot is at this angle and you're moving your leg down at this angle at this speed, how much force are you putting on the knee? All those things. If you move your knee this to the left and you stick out your thigh in this direction, where does your ankle go? And so he was, just a mathematical model that could just predict where different joints and bones and muscles would go in relation to each other based on what other ones around it were doing. And he took all that was known, and then he used motion capture technology to try and fill in the blanks, the things that weren't known. And so he would have an able-bodied person who still had his legs walk on the treadmill with motion capture balls all over different parts of his leg and force plates. And he tried to get all these variables. And also he would look at, he was measuring CO2 output with a mask to measure how much energy people were using when they walked. And so he had a model of, what an efficient leg, how it functioned. And then he tried to replicate the constituent parts with robotic components. So he used some of the directional measurement trackers that are used in guided missile systems. He put in there. He put just a lot of gears and motors and stuff. And one of the key insights and things that his leg did, his lower limb prosthesis, he calls it, is, like I said, every time we walk, we recycle about 50% of the energy from the previous step. And so he has, his legs do that. They absorb energy and release it. But also, when we jump, we basically, he didn't have the power necessarily to emulate or to do the same thing, to generate the same explosive force that our foot. I mean, if you walk, when you think about it, your foot kind of explodes off the ground. So what he had a insight by looking at actually fleas. So, my book is just filled with kind of interesting studies and things like, they studied how fleas are able to fly and fling their body weight, and they do it with basically a catapult mechanism. And so he built a catapult mechanism into his prosthetic leg, which is basically the motor feeds energy into springs, and then it releases it all at once. And when you think about it, that's what tendons do. When back in the olden days, when we had sieges of medieval walls, they actually used horse tendons as catapults, basically rubber bands. It's an interesting intellectual journey, a fascinating personal journey that he had. And then he was successful. He was able to build something that worked just like the real thing. He measured CO2 input, he measured force, he measured all of this. And when he puts it on, when other people put it on who've lost their limbs, often they start to cry because it feels like the real thing. And so, it's just an amazing story. And Hugh Herr also, now he he jogs. I mean, I just love that he used to dream about running behind his parents' house, and now he jogs around Walden Pond every day, and talks about what a beautiful run it is. And he climbs, and he has a TED Talk where he's dancing with people. And so these same insights can be used also, though, to build exoskeletons. He's built this exoskeleton kind of boot, which allows people to hike and expend less energy, because he's got these motors that feed energy into the leg with every step you take. The trick with exoskeletons is always to do this in a way that doesn't interfere with your gait and doesn't interfere with your mobility. No special forces guy wants to have his mobility, his ability to move in a firefight, compromised. So using these same, insights about biomechanics and how the constituent parts of the leg work together, he can build a device that you can strap on that actually feeds energy into the leg and makes it more efficient and makes you able to use less energy. So that's Hugh Herr. But I kind of just used him as a way to talk about this field of biomechanics. And also in there's people who are trying to make a human arm that functions like the real thing. That's something the Army, the military has funded because, so many people have lost limbs in Iraq and Afghanistan. But
the problem with these kinds of limbs is, especially I was talking with someone before, about the challenges around creating arms. And part of it is just, where do you put the power? How do you power these things? Because the human arm and all the range of motion we have in fingers and things, to replicate that is so difficult, but also requires a lot of power. And so there's a really fascinating number of different types of challenges that you run into when you're trying to create a mechanical limb.
Right. Yeah. I mean, I was alluding to that, I guess, with the catapult mechanism, because that was the primary challenge that Hugh Herr encountered, which was just he couldn't replicate the explosive force because he couldn't get enough power to the leg in a miniaturized form. So he used the catapult mechanism to gradually feed it in. But yeah, that's definitely true. I mean, there's the most advanced arm, the DECA arm. It's I think it's the same size and weight as a human arm, which was the challenge, but it's much less powerful. I mean, you give somebody a bionic arm with superhuman strength if you can plug it into a power source.
Right.
But so, I mean, that's the kind of challenge that people are still working on. And it seems to me that, power sources and battery size are continuously being miniaturized, and they're looking for other ways to wirelessly deliver this kind of stuff. But yeah, that remains, one of the biggest challenges. Another challenge is just, connecting it, to the nervous system so that you can get input both ways, which is something that people are working on, something I talk about in the book also. This is probably
a really good point to talk about Pat Fletcher, because she has a really fascinating story.
Right. Yeah. So Pat Fletcher. So actually I used her story, and again, this is kind of why I ended up building my book around stories of resilience rather than stories of augmentation. Because when you talk about somebody like Hugh Herr, it's like I could talk about exoskeletons and how they could allow us someday to, be all like Iron Man or lift concrete blocks while we're at work and stuff. And that's interesting, but it's nowhere near as compelling as somebody like Hugh Herr, who just, dreamt of running through his parents' field and had no legs and was able, through technology, to do that again. It's about getting back these abilities that bring us joy, and allow us to interact with the world. And the same thing with Pat Fletcher. So in my fourth chapter, it's in the sensing section it's on neuroplasticity, and it's when I start to talk about how the brain works, some of the stuff I was just saying. And Pat Fletcher had another compelling story, and she wanted to be a veterinarian, but she also loved nature, and she loved hiking, and she loved mountains, and she loved the water. But in order to go to veterinary school, she got a job working in a grenade factory, and down south, and there was a terrible industrial accident, some chemicals that I think one of the containers wasn't properly cleaned, and there was a chemical reaction, and anyways it exploded, and she woke up blinded, and basically, it shattered her dreams, just like Hugh Herr. legs, and she couldn't see, and she wasn't going to be a veterinarian, obviously. But anyway, so she adjusted to life and went about her business, and lived a happy life. But she missed seeing nature and stuff, obviously, and so one time, many years later, she was, I guess she still prided herself on her ability to dress stylishly. So she was looking for some sort of application online that, you could shine like a camera at something, like maybe a computer camera, and it would tell you what color something was, so you could match like, red pants with a blue shirt or something.
Right.
And she came across this program which claimed to be able to do that, but also claimed to be able to translate visual images into sounds. And she thought this sounded ridiculous. It was called Soundscapes. But she tried it out, and it totally blew her mind. And basically what it was is this guy in the Netherlands had developed this program. He worked for Philips as an engineer, but this was, I think, his PhD thesis a few years back. It's called a reverse spectrogram. And what it is if you ever seen like a James Bond movie and stuff where they're monitoring a phone call, and there's they take the sounds and they turn it into this visual representation, and you can find a signature of somebody's voice. This is the opposite of that. Basically what it did is it takes apparently our brain is capable of processing something like 30 different tones simultaneously. So what it does is it takes the pixels in a picture, it scans them very fast, and it will turn all the pixels into tones. So the lower the pixel is in the column on the picture, the lower the tone. The higher up it is, the higher the tone. The darker it is, the louder. Mm-hmm. The lighter it is, the fainter. Anyway, so it just sounds like a mass of sound, a wall of sound. But Pat Fletcher played one for herself, this soundscape, and it was of a picket fence where the gate was open. And she played it, and it totally blew her mind, because in her mind's eye, she could imagine the picket fence. It was almost as if she was seeing it. So whatever epiphany she had there, she felt like she was seeing a gate, and she went out and she downloaded the program. She went out, she got a hat, and with a little spy camera in it, she put a laptop in her backpack and headphones on, and she began walking around with this thing. And suddenly, she went to the dentist's office, and she could start to see the shapes of the wallpaper, and she could recognize the couch in her living room. And she just did this all the time, and eventually her brain adjusted, and she became better and better at making visual sense of this. And it wasn't an intellectual thing, it was an instant thing. And eventually she regained depth perception. She could actually see into a sink and see things in the distance. She could see leaves on the tree. And she claimed to have regained sight and been able to see with her ears, which seemed totally ridiculous on its face. But there's actually a field of research called where they're looking at something called sensory substitution. And she was recruited to come to Harvard Medical School, and they scanned her brain. And what they did is they played these soundscapes, and they noticed that when they played a soundscape, her visual cortex actually lit up. So the brain had learned to route these signals to her visual cortex. And when they just jingled a key next to her ear, that sound was sent to the auditory cortex. And when they played a soundscape and jingled the keys at the same time, they were both routed to the appropriate place. So somehow her brain had learned to recognize, what these soundscapes were, that it was visual input, and sent it to her visual cortex for processing. And this is really fascinating. It's an extreme example of what they call neuroplasticity, which probably a lot of people have heard about. But, what it gets to is just the fact that the brain is just a giant pattern recognition machine. And if we're exposed to enough stimuli enough times, it learns to sort it and classify it and send it to the correct place. So in a sense, Pat Fletcher really was seeing again. And so she was, the story I like to tell, just like Hugh Hare's moment where he's jogging, is that she went to a sensory substitution conference, because you can also, there's also, believe it or not, something called a tongue camera, where they turn visual stimuli into tactile feedback. And it turns out we have many different, our tongues are among the most sensitive parts of our body from a tactile perspective. So they just turn the visual stimuli into little electric shocks and electric stimuli, and you can actually see shapes using your tongue, which is kind of crazy. But so there was a conference on this obscure field, and she met the guy in person, the Dutch guy who had invented this, and they walked out into the desert together, and she was pointing at things and saying, "Yeah, that's a cactus. This is that. But then and he was amazed that she could see these things using the device he had made. And she pointed in the distance and said, "But what are those triangles?" And he said, "You can see those?" And she said, "Yeah, what is it?" And he said, "Those are mountains." And she started to cry because, she hadn't seen mountains and she loved mountains and just lots of great stuff. I mean, I love those kinds of stories, she was talking about how crazy it was. There was another blind guy who also, he had never seen before, and he came to Harvard also with her for the testing of this thing, and he saw steam rising up out of a coffee cup. Said, "What the hell is that?" Because you never think that, somebody who's blind doesn't realize that steam rises up off a coffee cup. So they'd never have reason for somebody to mention it to him.
Yeah, I suppose you would know that there's warmth above a coffee cup, but you wouldn't necessarily tie that at all to a visual reference point, or the visual reference point of steam, or even things like your breath that kind of fogs out on a cold day. That would probably be a new experience as well.
Right. Yeah, but so this has all sorts of implications for, there's a scientist in Israel who's trying to adapt this and use, instead of using instead of using a regular camera and converting it to soundscapes, he's using a infrared camera. So you could actually learn to see through walls. He calls it, I forget what he calls it, some sort of pun. Oh wait, maybe it's for your eyes only, for your ears only. I don't know. He's making a James Bond pun, but the idea, that you could see a heat signature through a wall using that camera is pretty amazing. And it just, it's a similar thing that happened with the cochlear implant, which I'll just tell you about that quickly, which is just, I talked to this guy, Mike Merzenich, who's one of the fathers of neuroplasticity, and what they wanted to do was, the way we get auditory stimuli is sound goes into our ears, and it basically, it hits these tiny little hairs in our ears and displaces them, and that sends an electrical signal eventually to a chain of neurons that gets to our auditory cortex. And so some people who are deaf they've lost those little hairs, or there's some problem where they can't get the auditory signals into their ears in the same way. So they made a cochlear implant, which instead of just amplifying sounds, actually tries to replicate those patterns of shocks to send, or patterns of stimulation to send the auditory signal into the brain to your auditory cortex for processing. And that's what the cochlear implant is. And he was trying to do that and trying to develop one, and they developed it, but he compared it to, basically trying to play the piano with your forearms. Like, the level of resolution that they could replicate was so crude compared to the real thing. But nevertheless, they invested a lot of money. They got people to try it out. And the patients came in and they said, "This is complete crap. I can't hear anything." But they kept the cochlear implants in, and about 6 months later, something amazing began to happen. They came in and said, "I can hear everything now." And what had happened is there was a consistent pattern that was sent to their auditory cortex. And over time, their brain had learned to make sense of this pattern. They'd learned, because the brain is a pattern recognition machine, they'd learned that whatever this crude combination of shocks was represented this sound, and this other crude combination represented another sound, and the brain had learned to actually make sense of this stimuli. And there's a famous scientist, actually the guy who invented, I think, the tongue camera, a guy named Paul Baccarita, and he said, we see with the brain, not with the eyes. And so if you can get that stimuli into the brain, you don't need the original sensory collection apparatus.
Yeah, I guess the eyes are a sensor, or the ears are a sensor. So all you need is the ability to create a new sensor that gives you reliable patterns. And the brain, more often than not, seems to be able to figure it out.
Yeah, and it's just a matter of training the algorithm, and so that's like when you talk about evaluating the hype and stuff. Basically, what I tried to do is to understand, how these things work, right? A lot of the hype has to do with where it will eventually go, right? So we don't have the capacity to develop a sensory collection device that is equal to the eye, and then get that same level of information into the brain. But we probably will be able to do that sometime, The resolution is constantly improving. Same with the ear and the cochlear implant. So when you hear about this hype, it's usually people speculating about something that's way ahead. We don't have but we have entered the universe of understanding how these things work. We just don't have the technological capacity to replicate it yet at the resolution that's necessary. But still, that's a huge advance forward. And what I found just so interesting, fascinating about this topic is that because of big data, because of sensing, we really are beginning to understand how things work together, how the human body and mind actually function at a level that we just didn't before. It was just guesswork. And that's what this book is about, really, basically, how, people understanding that and the kinds of insights.
Thank you so much for the book. It was a really interesting read. And there is, for the listeners, there is so much more in this book than we've been able to touch on today. It's well worth picking up. Thank you so much for jumping on the show today. Really appreciate it.
Okay. Yeah. Thanks for having me.
And if you want to learn more about Adam, his book, The Bodybuilders Inside the Science of the Engineered Human, his other writing, or some of the topics we've discussed in today's episode, we have links you can click in the show notes for this episode, which you can find on our website, scienceforthepeople.ca.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
Ken Thomas is a second-generation space engineer. He became a spacesuit project engineer in 1989, and his career spanned both the Shuttle Extravehicular Mobility Unit program and the Lunar Mars suit. He has taught at Central Connecticut State University and Johnson Space Center's NASA Academy, and since 1994 has worked as a consultant to the National Air and Space Museum's Space History Department. He's here today to talk about his most recent book, The Journey to Moonwalking, The People That Enabled Footprints on the Moon. Ken, welcome to Science for the People.
Thank you very much.
So your background is as a spacesuit engineer. Can you give us the quick hit about how that started and how you came to get into engineering of the spacesuit?
Well, my father was an aviation enthusiast who became a space addict big time, I guess, with the launch of Sputnik. I was not quite 7, but I remember vividly my father dragging me out into the front yard because he was very excited because Sputnik was visible because it had an elliptical orbit and it was decaying, and it was just perfectly positioned so you could see it in the night sky. And my father was just totally wired. And he was talking about we were on the verge of having people going into space and exploring space and everything else. And I mean, he's just, for him, this was the ultimate. And he was into it. And unfortunately, is joining the Gemini space program, which was at that point called Mercury Mark II, he caused us to have to move once. And then 2 years later, when that program wrapped up, it caused him to have to move again to join what he was hoping to join was the Apollo fuel cell program. Unfortunately, they found he had expertises that were more useful to his employer elsewhere, and so they paid him more money to not be an Apollo engineer, which made him rather disappointed. But he was still very much interested in space, and after he retired from Pratt & Whitney, he worked on the main lens of the Hubble Space Telescope. And so he was really into it. And because we had moved twice in 2 years when I was a kid, I wasn't really into it like he was at all. And ironically, I had an opportunity at work to join the space program, and I was considering it, and I happened to hear about it. And he felt it was a great opportunity, and I was kind of reticent because of what had happened to me as a kid. And I had a stepson, and I didn't want to put him through what I went through. And in sharing that, unfortunately, in retrospect, I said some things that I regretted a bit because I didn't want to imply that my father hadn't been a good father because he'd been a great father. But unfortunately, my father, just a couple weeks later, had a first-last heart attack. So that happened to be the last conversation I had, and I felt very bad about that. And before the end of the year, I was a program engineer on the Shuttle Extravehicular Mobility Unit, which is EMU. It's easier to say EMU than the other thing. And that's how I got there.
So what got you interested specifically in the history of the American spacesuit? Because given your background in engineering, one would assume that you'd write a very engineering-heavy book, one that talks about the engineering challenges about the spacesuit, which you do cover a bit in this book, but you chose to very much focus on the history and the people. So why did you do that?
Okay, because a NASA program manager and I, a retired NASA program manager and I, already wrote the nerdy book about all the technical information you would want to know and were afraid to ask about. It needed to be done because the people are the neat part of it, and they are neat people. These are ordinary people. They have families, they have lives, but they additionally help change history. And this is really important history because the Apollo 11 moonwalk was the most watched event in the history of the world.
So you cover a lot of people's contributions in your book. Do you have a favorite person that really stands out to you when you look back over the history of the spacesuit that made an important contribution that a lot of people don't know about?
I really like Lee Jennings. Lee Jennings was David Jennings' wife. Now, I spoke with her many, many times when I would call David to ask him a question. And invariably, she would be the one answering the phone, and she would say, "Oh, Dave's down in the basement. Let me call him." And she calls him, but anyway, so I'd be talking with her while David is coming. So I had the opportunity to talk with her many times. Now, the liquid cooling garment that was developed for Apollo, David was the inventor of record. Okay. Dave is a neat guy who, by the way, is still alive and living in New Hampshire. But he was a airborne Army paratrooper who dropped into Normandy, and then he again dropped into Belgium as part of Operation Market Garden and fought with Monty's forces. And he was an interesting character, but he's a very mild-mannered, very articulate, very detailed oriented person. But Dave can be very resolved in what he thinks should be done. It's a hoot, but in the developing of the liquid cooling garment, he wore one of his prototypes for 14 days to prove that you could wear it without removing it. So that he could demonstrate that you could wear it for 14 days in an emergency, return if you needed to, because once you launched, you were going out to the moon before you could come back. Mm-hmm. Okay. And so 14 days was, if you had a problem after you launched, it could be 14 days that you would have to be in a spacesuit. And so anyway, he wore his liquid cooling garment for 14 days to prove that it wouldn't cause you harm. Now, he proved that successfully, but it left little red marks on his body. Now, Dave, being a former Army Airborne trooper, he was not at all concerned about little red marks. However, his wife, by training, was a nurse, and she was. And so she bothered him incessantly about it, and she proposed putting a liner inside the liquid cooling garment, a chiffon liner. Dave thought it was going to be cause too much interference with heat transfer, and it would be a terrible idea, and yada yada yada. Anyway, she literally hounded him until he gave in and put a chiffon liner in one of the liquid cooling garments, and then they compared the one garment without the liner and one garment with the liner. and they couldn't measure the thermal loss difference. However, the guy that had the chiffon liner didn't have little red spots all over him. So consequently, the chiffon liner was a winner and got incorporated into the liquid cooling garment that was used on the moon. But it's even better than that, because the liquid cooling garments that were used in the shuttle spacesuits and the Skylab spacesuits and the International Space Station spacesuits all have chiffon liners. And, ironically, the liquid cooling garments used in the Russian Orlan spacesuits have chiffon liners. And even better than that, I forget the name of the Chinese spacesuit, but it's a derivation of the Russian Orlan. Its liquid cooling garment has a chiffon liner. I mean, this is okay, and this is all because of Lee Jennings and her perseverance against little red spots. And the history of the Apollo spacesuit is full of little things like this, because they were people, okay? And people, you talk with your wives, your husbands, and, there's interaction.
I was really fascinated to read throughout the book. And obviously now, having read the book, it makes so much sense how involved sewing was, and the ability to sew and the skilled trade of sewing was involved in the making of the spacesuit. But when we think of the spacesuit, we think of an engineered object in a very different way. We think of it as, tubes and things that twist and lock and filters and all that kind of stuff. But there's so much sewing and research into sewing and new designs and innovative ways of using fabric and innovative fabrics. And a lot of that work was done by women that largely have entirely missed the history book. And I really loved hearing about some of those women in the book and how many contributions they made to the suit.
Structural fabrics, okay. It's funny, but I had, working for Hamilton Standard, they had a composite manufacturing area. Most of the seamstresses, the old-time seamstresses that were there when I started working there, had originally started off in parachutes at Pioneer Parachute for the Korean War and the Cold War era, okay? And so consequently, their manufacturing was to government specs, which were geared around parachutes. And so consequently, that technology, they brought the technology to Hamilton Standard because that's what they were trained to work to. And they taught Hamilton engineers about specs on structural fabrics and how to select fabrics and how to manufacture all the intricacies associated with structural fabrics. They brought to Hamilton. Well, with International Latex, again, all the seamstresses were female, and when they got involved in the development of the spacesuit, they were training male engineers who knew nothing about sewing. And so consequently, there was, on their side, they additionally had the women transfer information to male engineers going on as well. It's kind of neat to have seen it in two places happening simultaneously. And then, of course, there was a cross-pollination between Hamilton and International Latex as they were fighting, but still working semi-together on the Apollo spacesuit program. And one of the women I really like on the ILC side is Ellie Foraker, who I've known so many people that knew her. I never had the privilege of knowing her personally, but one of my friends happens to be a female engineer at ILC Dover, and Ellie not only took and cultivated male engineers, she took great pride at helping and cultivating female engineers. And International Latex, ILC Dover, did have a lot of female engineers. They tried to cultivate female engineers much better than Hamilton Standard did. And it's kind of neat. And of course, Ellie was instrumental in many different points. She stood out with helping save the Skylab space station. Okay, the space station was overheating and going to be destroyed, and she helped fabricate and design an umbrella thing that would go through a hole and then cover over the lost insulation so that they could cool down the space station and make repairs. And she was, just an absolute marvel and an absolute great human being, and she's a part of history. And these people, unfortunately, don't get to show up in the history books. it's terrible because every great event is done by people. And maybe you hear about a general or a president or, but that's nothing. I mean, the people that make it happen are the people on the ground. And that whole story of the Apollo spacesuit is basically ordinary people doing extraordinary things, coming up with ideas. And, it's just a great story.
I didn't realize until reading this book how much competition, and obviously there was competition between companies, but there was actually like a structured competition that was run in order to build these suits.
Oh, yeah. Well, if you don't know what is the best way of doing it is have everybody do their best and then test it and see what works and doesn't work. And they did that over and over again. The Hamilton Standard funded internal development and compared the testing to what was on the program. NASA wanted quantitative data, so that drove additional competitions from the various manufacturers. And then in 1965, NASA decided that they were going to select the suit for the A5H configuration. They were going to have a competition and go with what was best from that competition. And it was a very iterative process, but in the process, they developed some interesting spacesuits and technologies.
Yeah, for sure. It was a really great, almost visual example of how slow science moves, especially science that is done by so many people working together, where it's one step at a time. You really literally have to isolate one thing and do that one thing and figure out how to do that one thing. And then you add on another thing. And that process is just sometimes excruciatingly time consuming and can take an astonishing number of people to make it happen.
Oh, yeah. And the real problem is you don't know what you don't know. So until you have a complete article and you test it, like they did in late 1963, they got the first full complete spacesuit system for Apollo, and they tested it. And one of the things they discovered was their life support requirements were all wrong. Now, they had a life support system that attached to the suit, which met all requirements, but the requirements were wrong, so the design was useless. And on the pressure suit side, the suit didn't meet the requirements, and the testing that was conducted then the coming months after that proved beyond a shadow of a doubt that it wasn't ready for prime time. And so consequently, everybody went back to the drawing board.
It's so great to see, though, that everybody did go back to the drawing board, and we did end up with spacesuits, and we did walk on the moon, and we continue to use really cool spacesuits to this day, which is so cool.
Oh, yes. And we're going to continue. And I am an inventor of record on 3 international patents for lunar Mars spacesuit technologies. 2 are my ideas. One, the idea was originally somebody else's, but there was one. He had a problem. It wouldn't work the way he envisioned it, and he showed it to me, and I could see very quickly that it wasn't going to work. He thought I was crazy, and then he played with it, and then he realized I was right, and I suggested how we could make it work, and we then ran it past management, and that ended up being a patent. So anyway, that was the third and last one. But unfortunately, we are not going back to the moon anytime soon, or Mars. So consequently, there's no money to continue such things. But we will get there.
We'll get there someday.
And they will be looking at the spacesuit efforts that had been conducted in the past. Of course, that past might be 20 or 30 years in the future, but nevertheless, they'll be looking at the past and learning what they can from it. And by leaving a trail, that'll be part of what happens to get us back to the moon and Mars.
Ken, it's a really interesting book, and lots of really interesting people that I don't think would be known about without your book. So thank you so much for writing it, and thanks for coming on the show to talk about it.
And thank you.
If you want to know more about Ken Thomas or his book, The Journey to Moonwalking, The People That Enabled Footprints on the Moon, we, of course, have links to click on our website in the show notes for this episode, which you can find at scienceforthepeople.ca. Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.